So yeah, question 6.13 on the homework, we're given the information, we've got a 36 watt light bulb, and they tell us that 1 watt equals 1 joule per second, right? Generates violet light with a wavelength of 420 nanometers. How many photons of light does a lamp generate in 1.7 seconds? So we need to basically go from, well, it's a 36 watt light bulb, and we know 1 watt is 1 joule per second. So we know 36 watts would be 36 joules per second. And we run this light bulb, we turn the light on for 1.7 seconds. So, all right, 1.7 seconds is how long the light's on. So seconds cancel out. We're going to get the total joules that are given off by the light. So 36 times 1.7, right? Approximately 61.2 joules of energy are released by this light in 1.7 seconds. To find out how many photons of light that requires, right, we have to go back to the wavelength of light to find the energy of that light, because that's the energy for 1 photon. We'll find that energy, and then we're going to have to divide to basically see how many times does this little photon and its tiny little energy need to go in to make 61 joules of energy. So 420 nanometers, right? I know for every billion nanometers, I have 1 meter. So we're 4.2 times 10 to the minus 7 meters is our wavelength. The fastest way, right, that I would go about this, I would say the equation I would use next, energy equals Planck's constant, the speed of light over my wavelength, because we know wavelength, we know Planck's constant, we know speed of light, we can find the energy for 1 photon of light. So energy for a photon equals Planck's constant, 6.626 times 10 to the minus 34 joules times seconds. Speed of light, 3 times 10 to the 8 meters per second. Over my wavelength, 4.2 times 10 to the minus 7 meters. Check our units, right? We're going to multiply the top two. When we multiply, seconds cancel out, and then we're going to divide the two top and bottom. Meters cancel out, and that's good because we're looking for energy, right? Energy of this 1 photon. So I multiply those two together, 6.626 minus 34 times the speed of light, 3 times 10 to the 8, and divide that by my wavelength, 4.2 times 10 to the minus 7. Yeah, I get this tiny little energy, 4.73 times 10 to the minus 19 joules. But the key is that's the energy for 1 photon of light. We need to figure out how many photons total, right? So we need to figure out how many times this energy goes into 61. So I've got 61.2 joules, and I know for every 1 photon, right, we've got 4.73 times 10 to the minus 19 joules. So joules cancel out because we're looking for a total number of photons. So 61.2 divided by that, and yeah, we get a huge number. 1.3 times 10 to the 20 photons of light. I would go with two significant figures because 36 watts is two significant figures. 1.7 seconds is also two significant figures, so I would report the answer to two significant figures. But what makes this problem a little bit challenging is, right, they give us the watts. Watts are joules per second, so I can turn watts into exactly that, joules per second. Then we know I run the lamp for 1.7 seconds. That gives us a total energy output of 61.2 joules. From there, I know the wavelength of light, and I know I can relate that wavelength of light to the energy of light. The key being that's the energy of one photon. So now I have to say, okay, one photon is this much energy. I need 62 joules. How many photons would I have to add together, right, to get that total energy?
So I'm like confused by like, how do you know like when energy is being released?
Yeah, so in this